Just close your eyes and listen this technology. Apache Kafka. In modern system, managing data flow between multiple applications has becoming increasingly complex. If you are working with a data intensive application or building event driven architecture, you have likely encountered Apache Kafka. But what problem does Apache Kafka solve and why it has become such a fundamental tool in modern architecture? The data integration challenge. As its core, software system need to move data from source system to target system, often with transformation or aggregation along the way. In the simplest form, this might involve a straightforward point to point integration. However, as organizations grow, this simple pattern rarely sufficient. Consider a modern e-commerce company with its source system, customer facing web application generating user activity data, mobile app tracking user behavior, payment process system recording transaction, inventory management system tracking stock level, order fulfillment system tracking shipment, target system, data warehouse for business intelligence, real time analytic platform for monitoring, customer relationship management system, fraud detection system, recommendation engine, email marketing platform. Each source system might need to send data to multiple targets. For example, when a customer places an order, the data warehouse needs it to the historical analysis. The fraud detection system needs it for the real-time verification. The CRM needs it to the update customer record. The inventory system need it to the adjust stock level. The marketing platform need it to trigger follow-up email. This type of system could look sometimes very messy. The problem with the direct integration approach introduces several critical challenges. Tight coupling. System becomes tightly coupled, creating a brittle architecture where changes in one system can cascade throughout the entire infrastructure. Complexity at scale. As system multiply, the number of point-to-point connection grows rapidly. With 5 source system and 6 target system, you could potentially need up to 30 different integration, each with its own maintenance requirement. Maintenance overhead. Managing and monitoring this direct integration become increasingly difficult. Each connection might require custom error handling, data transformation logic, monitoring and alerting, rate limiting and back pressure mechanism. Limited flexibility, making changes to data flow or adding new consumer require coordinating with multiple teams and systems. For instance, adding a new analytical service would require new connection to all relevant source systems. Entire Apache Kafka, the decoupling layer. This is where an event bus like Apache Kafka comes in. Instead of direct system to system communication, Apache Kafka introduces a powerful publish subscriber model that changes how systems interact. Apache Kafka was developed by the LinkedIn engineer in 2011 to handle their large scale data feed. It was later open source and become a top level Apache project, now widely used across industries for real time data streaming. How Kafka transformed the architecture. Kafka acts as a central system for your data, providing decoupling communication, produce source system, publish data to flow without the knowledge or downstream consumer. For example, the e-commerce platform can publish order events without knowing whether they will be consumed by the analytical system, fraud detection, or both. Unified integrate interface. Consumer target system retrieve data from Kafka using a standardized interface, eliminating the need for the custom integration code. The fraud detection system can consume the order event using the same interface as the analytical platform. Scalable design. New producer and consumer can add it without affecting existing system. For instance, adding a new recommendation engine only require connecting to the Kafka, not to the each individual source system. Data persistence. Unequal, unlikely traditional message queue. Kafka stores data for configure retention period, allowing for the reply and multiple consumption pattern. This enables serious like reproducing historical data after fixing bug, adding new analytical system that needs historical data, recovering from failure by replying miss event. This result architecture became more resilient, scalable, and maintainable. With this foundation established, let's dive deep into the Kafka architecture and core concept to understand how it's achieved this benefit. Kafka topics. A Kafka topic is named channel that stores a sequence of the messages into a specific order. Think of it as a log where messages are continuously append and stored. Each topic has a unique name like payment events, or user activity. Producer write messages to topic and consumer read those messages independently. For example, a payment service might produce message to the payment topic while fraud detection and analytical service consume from it. Topics are format angiotics supporting and data structure for simple text to complex object. Kafka topic partition. Let's dive into how topic is structured. A Kafka topic is divided into multiple partitions, each acting as an order sequences of messages. When data is written to a partition, it assigns a sequence ID called an offset. This offset uniquely identifies each message within its partition. Key propriety Key properties. Message ordering is guaranteed only within the partition, not across partition. Once written, messages are immutable, cannot be changed. Offset are never reused even after message deletion. The producer decided with partition to write to. More on this into next section. A consumer subscriber to partition or the multiple partition within the topic. More on this on consumer section. The diagram shows the topic with three partition with the message ordering by their offset with each partition. This dotted line indicate whether the next message would be written into an each partition. Kafka producer. Now let's talk about the Kafka producer. A producer is a system that writes the data to the Kafka. Producer write message to the specific topic partition. Each messages has an optional key that determine the partition assessment. Messages with the same key are set to the same partition, ensuring the ordering processing of related messages. When a key is provided, the detention partition is completed for the hash of the key. This ensures that all the messages with the same key are sent to the same partition. If no key is provided, messages are distributed across partition in a round robin fashion. This was all partition get an even share of the data. However, the order of the messages in this case is not guaranteed. This makes key important when message order matters. Example, events from the same user devices. All the data is serialized to byte before sending using the hash by default. The producer handles this process. Message routing in Kafka based on the key. Message from user 123 consistently go to the partition 0, while user 456 message go to the partition. Return in each partition message received sequentially offset, maintaining the order for each user event. For message without the key into Kafka, the distribution follow a round robin pattern across partition. In the topic with two partition, message 1 goes to partition 0, message 2 goes to partition 1, and similarly so on. Kafka consumer. A Kafka consumer pull data from the topic partition rather than the having Kafka push data to it. The pull model lets consumer control the data consumption rate and processing. Consumer can subscribe one or multiple partition depending on their need. Since Kafka stores data as the binary, consumer must describe is using the correct schema and deserialization method. Maintaining consistent data schema throughout to topic lifecycle is crucial. If schema changes are needed, create a new topic rather than modifying and estimating one to avoid breaking consumer. Consumer group. Consumer group in Kafka allows multiple consumers to work together to process data from a topic into a distributed manner. When a topic has a multiple partition, consumer into a same group divided this partition along themselves. Each partition is read by the one consumer within a group. This is avoid pre-processing the same data within the group. However, one consumer can read multiple partition. You can have more consumer into a group that you have partition. In this case, you will have inactivity consumer within your group. If a consumer in your group fails, then the inactivity consumer can take over. Multiple consumer group can read from the same topic independently. Why would you want to have a multiple consumer group? Suppose you have two series service like the analytics and fraud detection. You can create a group for each services within the each group having a multiple consumer, allowing you to distribute the processing of the data for each services. You can process multiple partition in parallel. In the example above, we have a payment system topic with a 4 partition. We have an analytical group and fraud detection group. The analytics group has 2 consumer, each takes 2 partition each, and the fraud group has 5 consumer. The first 4 consumer are taking a partition each. The 5th consumer in the group is idle and will become active if the consumer within the group fail. To use the consumer group, you can use the consumer property group.id. Consumer offset. How do we know when a consumer has successfully read into a partition topic? When a consumer from a consumer group reads data from the topic, it will commit the offset from which is last read into an internal Kafka topic called the consumer offset. This is to keep the track of the whether the consumer should pick up from the next time is read the data from the Kafka. Java consumer automatically commit offset to the Kafka, but this can also be manually triggered. At least once prefer. This is automatic method too. With this mode, an offset is committed after a message has been successfully processed. If an error occurs during the pre-processing, at least once. This is the automatic method too. With this mode, an offset is committed after a message has been successfully processed. If an error occurred during the processing and you need to restart you can reply to it exactly where you last were. At most once commit offset as soon as the message is read. If the processing goes wrong, there is a chance you won't reply to the last event. Kafka broker and cluster. A Kafka cluster consists of the multiple brokers working together to store and manage the data. Each broker is responsible for storing a specific topic partition, ensuring the data is distributed across the cluster. When a client connects to any broker in the cluster, they gain specific to all broker through that connection. This is known as the bootstrap connection. Broker and topic. So how are the topic and partition stored into a Kafka cluster? Say you have a topic called the user event topic with 3 partition and another topic order topic with a 2 partition. Say you have 3 broker. A broker is essentially a service that can store their data from multiple partitions from different topics. Looking at our example now, user event topic has 3 partitions distributed across the broker. Order topic has 2 partitions distributed across the broker. Each broker acts as a storage unit capable of holding a partition from any topic. The broker based architecture enables 3 key benefits. Load balancing. Data stores into a distributed across multiple servers. Parallel processing. Multiple broker can handle requests simultaneously. Horizontal scaling if you add more broker as your data grows. Topic replication. One great aspect of the Kafka is that is fault tolerance. So if a broker goes down, the idea is that you don't lose an access to your data, but how? Kafka achieves fault tolerance through a partition replication. Each partition is replicated across multiple brokers in your cluster to prevent the data loss during the broker failure. Key points about the replication. Once broker service as a leader for the each partition, other broker maintains synchronization copies of the partition. Producer writes the partition leads with an additional ability to write to the synchronous replica. Consumer traditionally reads only from the leaders, but since Kafka 2.4 Plus can also read from the ISR, the replication factor setting control how many copies of each partition exists. Production environment should be 1. Local development can be 1 for simplicity. We can see for the Example, if broker 1 goes down, we don't lose access to any data because partition 0 data is still available for its replica on broker 2 and 3. Partition 1 leaders is 1, broker 2 so is unaffected. In this case, a new leader for partition 0 will be elected automatically. We will get into more into zookeeper section. Producer acknowledgement and topic durability. Producer acknowledgement solve data durability and consistency challenge in distributed system. Here why they exist. Without ask, you wouldn't know if message were actually received by the Kafka, data was properly replicated before a broker failure, message were lost in transit due to the network issue. Kafka producer can be configure acknowledgement level. Acknowledgement equal to 0. Producer do not wait for the right confirmation. Acknowledgement word. Producer waits for the right confirmation for only the leader of a partition. Acknowledgement all. Producer wait for right confirmation from the leader plus replica. Zookeeper and K-Graft. Zookeeper is a service that manages the Kafka cluster state, monitoring broker health and handling the leader action. When broker fails, it's been integral to the Kafka distribution to coordination since the beginning service as the central coordination for the cluster. However, Kafka is evolving beyond this dependency. Kafka 3 introduced Kafka Raft as an alternative to the Zookeeper, and Kafka 4.0 will eliminate the Zookeeper dependency entirely. This changes streamline the Kafka architecture by handling cluster management internally rather than relying on the external services. And this is the end of your video. I hope it helped you to better understanding Kafka and its capability. So what are your, if you have any question or you want to suggest anything, please let me know in the comment section. Happy listening.